tasks such as manufacturing, assembly, etc. The main issue in this context is that automation and humans have different kinds of decision-making models. For example, automation is good at number crunching, and humans are good at decision-making with quick mental models. So, so in a collaborative decision-making framework, both these strengths can be utilized. And one more thing humans are good at is generalization. For example, if a system is trained to process, let's say, retinal images from data collected from a hospital, and then the system is deployed in some other hospital where the data is generated in different conditions, let's say different lighting conditions or so on. The performance is not the same. Performance of the AI system is not the same. So, but humans are good at generalization. That's what this means. So, a medical student who learns how to read or how to read X-rays, he has that knowledge with him wherever he goes. So that's what I meant when I said humans are good at generalization. Yeah, some other applications for human AI teaming. So some things that come to mind include search and rescue missions, and anywhere large amounts of data needs to be processed, but at the end of the day, it involves some kind of a risky decision, so you might need human review. So you can think of any number of such applications in reconnaissance, intelligence, and for defense purposes and so on. For example, identification of hostile targets, automated mine detection. Yeah, and you can think of some applications in autonomous or semi-autonomous navigation systems. Yeah, so we are looking at this kind of a setup. So there is an AI and a human reviewer, and there is a supervising system. Tasks are, there is a batch of tasks incoming, and the supervising system has to decide on which tasks to be referred to the human. That is the question we are going to look at. And yeah, and prior to that, the AI or the automation, it takes a first pass at all the tasks. That's the assumption, that the AI would be doing most of the task processing, and only very important, very risky decisions must go to the human. Yeah, so what are human factors and why do they affect the performance of, yeah. Yeah, so no, this is not a feedback-based learning. There is no learning happening here. Here we are simply looking at which tasks must be reviewed by the human. Automation has processed the tasks, but you would like the human to review some of the tasks and take a final decision. Yeah, yeah. Yes, essentially that. But the catch is that there are human factors involved. So why are human factors involved? Essentially because there are physical and mental consequences for the actions that are being taken by the system. So what are these human factors? Mental workload, fatigue, belief, trust in the automation, self-confidence. So I can give you one example where these factors will play a very important role in the performance of the system. So for example, you look at a scenario like this. So there is a victim here, and there is a search and rescue team who is making use of drone footage to first of all find out and reach the victim. And here in this application, time is of essence. So any time lost is going to have unwanted consequences. So let's say a drone and an AI system is assisting the team, and footage is being collected and processed by the AI. Suppose the operator who is operating the system, the human operator, he decides that he doesn't trust the system enough. So he doesn't trust the system that it has properly identified whether in this footage the victim is there or not. So the operator might decide to take a relook at some of the footage. So this will, in this application, this will lead to delay, and it can lead to possible death of the victim because of the delay. And similarly, mental workload. If the operator has high mental workload during this operation, there is, for example, there is tunneling effect which comes into play usually, and the details on towards the edges of the footage will be blurred in the experience of the operator, and he might take wrong decisions. So essentially, the innovation here which we are looking at is not from the AI perspective. AI is a pre-trained AI. We are trying to model the impact of the human factor. Yeah, so all these factors are very complex constructs, and they have multiple definitions and models in the literature, and there is a lot of debate on how to model and measure them. Yeah, so in this work, we are only looking at mental workload. So what is mental workload? The notion of mental workload has been defined to answer these questions, these kind of questions. So how busy is an operator? How complex are the tasks being performed? Will the operator be able to respond to an emergency event? These kinds of things. So most of these work in this area has been pioneered by NASA, because they were interested in how these factors would impact their missions. Yeah, so usually there are varied notions in the literature on how to define and measure mental workload. And most of the definitions are based on using mental resources such as attention, executive function, memory, and so on to define mental workload. And broadly, 3 categories are there of measurement. Like self-report measures, they give the operator a questionnaire, and depending on the answers to the questionnaire, they try to assess the workload. That's one kind. And physiological measures, you have measure pupil dilation, pulse rate, heart rate, variability, and so on. And yeah, and also the most obvious thing is primary task performance measures. So how well is the task being done? Yeah, you can measure that. Yeah, so I would like to differentiate between mental workload and task load. So mental workload is a complex cognitive construct. On the other hand, task load is defined as the number of tasks that are assigned or being done in a fixed period of time. So mental workload can be a nonlinear function of task load, right? But the main thing is that task load can be directly measured. Mental workload, it cannot be directly measured. And so can we use task load as a handle on mental workload? So under some conditions we can, depending on depending on the task. We look at an example of such a task where mental workload is almost linearly dependent on task load. Okay, so this simplifies the model and avoids measurement problems. So we'll be modeling the human as a task load dependent performer. Any questions until now? Comments? Okay. So broadly, this task allocation problem classes fall into 4 categories, 2 on the human side and 2 on the automation side. On the human side, there can be human as an interventionist and human as a non-interventionist. For example, you have a team and working together, AI and a human. The human can redo some of the interfere with the task being performed, and also the human can redo some of the things. Also, as a non-interventionist, the human might not intervene per se, but when some task allocation has been done, they might not adhere to the assigned task load or so. So this is an example of human being a non-interventionist. Yeah, and so from the automation side, we can have 2 classes of the literature. So blind task allocation and informed task allocation. Blind task allocation is focused on figuring out the optimal workload or optimal task load distribution. So what fraction of the task load should go to the human and what fraction for the automation. But yeah, and informed task load is a more intelligent version where it looks at each task to decide whether or not it has to be sent to the human. So we will be using a blind task load method as a baseline and come up with our own informed task load allocation. Yeah, let's formulate the problem. And so this is the setup. So there is a batch K of tasks coming in, and first the automation, the AI takes first pass at all the tasks, and then the supervisor has to decide based on the information provided by the AI which tasks need to be sent to the human reviewer. And we look at binary classification tasks. So the problem statement is simple. What is the optimal subset of tasks to be referred to the human? So these are some important model assumptions about human decision models. So the first one is the human decides between the 2 hypotheses based on their own observation alone, and they don't have access to the automation's observation. This is obvious because we don't have usually access to the feature vectors of the automation while making such decisions. And most important assumption we are going to make is at the bottom is that at the minimum task load, the human is better than the AI, or else there is no meaningful way to formulate this problem. So at the minimum task load, the human is better than the AI, and at the highest task load, the human can be worse. So the AI falls within the range of the human's performance limits. So this is an assumption that is needed to make this problem meaningful. Yeah, let's look at some details. Okay. Yeah, if more tasks are given to the human, uh, the workload increase. Yeah, the performance changes with the task load. I will give you a real world example of that. So yeah, this is the model broadly. So the AI has an observation model and a decision model, and the human has an observation model, decision model. In addition, they have a task load dependence. So the observation model and decision model usually it's very difficult to measure. So what do? We just use what can be measured. What can be measured, as we earlier mentioned, task performance can be measured, right? So as we are dealing with classification tasks, what can be measured? Task performance as, so classification performance can be measured, right? So, and how can they be represented? As for binary classifiers, they can be represented using true positive rate and false positive rate. So what we are essentially saying is that if we have a function, a true positive rate function as a function of task load, and false positive rate function as a function of task load, we can represent the performance of the human as a classifier. Yeah, so let's look at some notation. And so there are, yeah, the batch K of tasks, and there are two possible states, hypothesis and H0 and H1, and there is a prior on the hypothesis, and they come in, and all of them go to the automation. And for task K, YAK is the observation, and the system computes a posterior belief, PAK, and which is essentially a posterior probability, and based on this, this decision is taken. So this is kind of summarizing all the decision making that goes on. For example, even if the input is an image, ultimately the observation will be a high dimensional observation, but at the end of the day, you have to compute a posterior belief about the class and then make the decision. So they are independent, identically distributed. They are from the same distribution, but not the same, right? Yeah, so why did you get that out? Okay. Yes, I mean, they are not identical in the sense that they are from the same distribution, but you would have different posterior beliefs after looking at each. Let's say you have an image, and you're asking, you have an image of a flying object, and let's say you ask the system, is this a drone or a bird? now you'll have different belief levels, posterior belief levels about whether it's a drone or a bird. Yeah, but here the question is, even though the performance of the system is static in the sense that it is not task load dependent, the human's ability to do this task at their lowest task load level is better than the system. So there is this cost associated with the automation's decision. So PAK is our belief, posterior belief, and DK is the decision which is made based on this belief. And so this cost is a function of these two. Okay, so then similarly you have an observation model for the human, and there is a different observation vector or feature corresponding to each task load. For example, the same image, if it is shown to the human under higher mental workload, higher stress, they will find that the tunneling effect has blurred out the edges of the image. So for the same task, you can have different observation. So yeah, and then there is a decision set. There is a decision, but this decision is not exactly known a priori or even a priori by the AI. So, and we don't even have a proper model for that. So all we have is a performance model. What is a performance model? You have this true positive rate and false positive rate as a function of task load. So true positive rate is defined as this. So that the true hypothesis is H1, and the human has labeled it as H1, and the false positive is true hypothesis is H0, and the human has labeled it as H1. So now these are not known for the system only knows these two functions a priori. So what happens to this, the cost of the human's decision? It has to be estimated based on the belief of the AI about the human's performance ability for this task. Yeah, we'll see how to compute this cost. Let's look at a model which is to represent this. So let's say, instead of a high dimensional observation model, let's look at a simple model to understand the trade-off. Okay, so there is this, there are two hypotheses, and yk is the observation for task k, and it can be drawn from either hypothesis 0 or hypothesis 1. So the solid red curve is the distribution under hypothesis 0, observation distribution for observation distribution for hypothesis 0, and this dotted red line is for hypothesis 1. Okay, and you can compute how the performance metrics for each of these curves. But on the other hand, the human has a task load dependent observation. For example, for hypothesis 0 and workload 1, task load 1, he would have this curve, and this for hypothesis 1, this curve. So now you can see that when you compute the true positive rate and false positive rate for a given prior, you can draw a threshold and compute the true positive rate and false positive rate, right? So you can see that as task load increases, the variance of the noise increases. So here the variance of the noise, additive noise, is a function of task load. This simple model can be used to represent the trade-off between the decision makers. Any questions regarding this? Yeah, so, and this model is also useful because, see, even if the input observation is a high dimensional input like an image, the when you come to the last layer where you have to decide about the probability of it being one of the classes, the pre-activation inputs to the last layer can be approximated as a Gaussian random variable. Yeah, so this is another representation of the trade-off. So in our previous slide, depending on, suppose you assume that the human is randomly drawing thresholds instead of being an optimal threshold, Bayesian optimal classifier. You could draw different thresholds, and you would be moving along one of the curves of the receiver operated ROC curves. So, but we can, to simplify the problem or the analysis, we can assume that the human is doing their best at their given task load. So even if they have a certain mental workload, at that mental workload, whatever best can be done is being done by the human. If we make that assumption, we can simplify the problem like we did. We won't require to measure all these ROC curves, and it is enough to measure just the two functions which we talked about. Yeah. So there are, for each decision, there are 4 costs, obviously, and because it's binary classification, true positive, false positive, true negative, false negative. And the values of these depend on the application. So usually true positive and true negative, because they're correct decisions, the cost is usually 0. But false positive and false negative usually depend on the application. For example, false negatives are cost of a false negative is very high in a defense application, higher than false positive. For example, I don't want a drone to be classified as a bird. That's a false negative, right? Because yeah, it's like life or death. And false negative, the cost of false negative can be less than false positive in some medical scenarios, where suppose a person is, suppose the test says that a person has cancer and it's a false positive, and the treatment for cancer for a person who doesn't have cancer is pretty horrible. So mistreatment is very dangerous. So in that case, it depends on the perspective of the designer of the application. So yeah, essentially this is it boils down to this expression, the cost of the automation's decision for task K. So it's a function of the belief which is computed. We have this, and we have a simple decision rule again. You have 2 functions from this, and whenever this function is less than this, you assume that the decision is H0, and otherwise it's H1. And you have an optimal cost, which is this. So on the other hand, from the for the human, we compute the cost of the classification decisions solely based on the belief of the AI and the performance model of the human. So we have an expression for the cost of the human. So for task n, which has been referred to the human, you can compute an expected cost conditioned on the task being from hypothesis 1 and then conditioned on the task being from hypothesis 2. So you get the total expected cost, and then you get the sum. You take the summation on all the tasks that you want to refer to the human, and compute the expected cost you would have if this subset n has been referred to the human under task load W. Is it okay? Do you find the so this is the expected cost under the belief that the task is from hypothesis 1, and this is the expected cost under the belief that task is from hypothesis 0, and this is an additional penalty which for referring it to the human. Yeah, and yeah, obviously the optimization problem is to minimize the total cost, what should be which subset should be sent to the human, and what should be the decisions of the classification decisions of the automation. So here is an example which will help us appreciate the trade-off. So this is the cost of, sorry. Yes, okay. Yeah, they are based on the application. These are, you can think of them as hyperparameters, but essentially they're pre-specified by the designer of the application. So yeah, like I was saying, in a defense application, you would have false negative much greater than false positive, and so on. Yeah, so you have these black lines are the cost of the task, the automation's classification cost as a function of the belief, and each of these lines is for a fixed task load. So you can see if you fix the task load, you can have two thresholds. Let's say you fix this task load, you have two thresholds, and you'd say that anybody who falls within those task loads can be sent to the human. But the problem is there can be more than those many tasks which are falling within these thresholds. So we have a simple, we prove a simple theorem which says that define an index like this, this is the cost, classification cost of the automation, this is the classification cost of the human under task load W, and this is the penalty for referral. This is if you use this as an index to rank the tasks, and for under a fixed task load, you will be minimizing the total cost. That is the theorem which we had proved, and yeah, the theorem is the proof is quite straightforward. I will skip it, and then we have an algorithm to compute the optimal task load. So we compute the optimal task load using the theorem that under a fixed task load, if you use this index to rank the tasks and send the first W tasks, according to that ranking scheme to the human, you will be minimizing the total cost. So we have three possible referral strategies which we had compared. So one is the blind allocation one, which is which is based on the human performance model, but it doesn't care about the uncertainty in individual tasks. It is only worried about what is the optimal workload on an average. And the optimal allocation is what we have looked at, and a static allocation scheme which we had proposed as a fixed task load variant of the optimal allocation scheme. So what is the use of this? So in the optimal allocation scheme, if there are subsequent batches coming in, and if the optimal allocation scheme sends different amounts of task loads to the human, and there's a variation in this task load, it has been observed in some studies that this induces fatigue. So if the task load is varying too much, that induces fatigue. So we came up with a static fixed task load variant of the optimal workload. And then let me show you some results. Yeah, before I show you some results, so these three, blind allocation, optimal allocation, and static allocation, we want to compare in terms of different parameters. So is the allocation based on human capability? Yes. So in blind allocation, for the task load levels, yes, but for individual tasks, it doesn't care about. So yeah, in optimal allocation, yes, and in static allocation also, yes. So, and the task load is constant across batches for blind allocation and static allocation, and for optimal allocation it varies with batches. For computation, we have this as offline. So the blind allocation scheme looks at the performance models of the human, and it computes the optimal task load, and then that task load is maintained across whatever batches that come in, and yeah, you choose the tasks. You can choose the tasks either randomly, or you can choose it based on the ranking scheme we proposed. But here in blind allocation, it is chosen randomly. So yeah, in optimal allocation, the computation is done online, and in static allocation, the task load is computed offline. So it's computed offline through, you need some data to do some simulation to compute this task load. But the optimal task subsets are, once that task load is fixed, for every batch you use the referral scheme to compute the optimal subset. Yeah, so assuming that, so I'll show you some simulations, and then we'll look at some experimental results. So here we assumed that a Gaussian observation model, which I had shown you earlier, and assumed that the human is a Bayesian classifier, and done these simulations, and it shows that the optimal allocation and static allocation, they have similar performances, and the blind allocation is costlier than the optimal allocation. And in terms of task load, the blind allocation fluctuates much more than the optimal allocation for different problem instances. So let me show you the results of an experimental study we conducted. So we considered this setup. So this is the simulation of a radar screen. So this is shown to operators, and if you click upon one of these targets, you get to see these parameters. And using these parameters, you have to decide whether this target is hostile or non-hostile. And now, and we provided a decision rule along with it to decide whether it is hostile or non-hostile. Now, as I was saying earlier, this is an example where you can assume that mental workload will increase with task load. Suppose you have to finish all these targets in 2 minutes, and if you fix the 2-minute time interval and increase the number of tasks, your workload, you can assume that the mental workload increases. Yeah, so we had done 2 experiments. One experiment to estimate the parameters, to measure the performance models of the human, and the second experiment to compute, to compare 2 of the allocation schemes, blind allocation scheme and optimal allocation scheme. So yeah, this was the actual setup shown, and first we measured true positive rate and false positive rate for different task loads. So we said 6 tasks, 9 tasks, 12 tasks, and 15 tasks. So results are here. So we had 28 participants, and this is an IQR spread of the data. You can see the mean decreases, but later on we discovered that some of the participants haven't done all the tasks. I mean, they haven't completed even 50% of the tasks, so they were not considered as valid samples. So when we consider only the valid samples, we get this pattern. So you have 90% true positive rate, and it decreases at 9 tasks, and it further decreases at 12 tasks, and at 15 tasks it increases. So surprisingly, the assumption that the task load, as task load increases, performance always decreases, did not hold here. And the intermediate values, for intermediate task load values, we used interpolation. So, and similarly, you can see for false positive rate, it has increased from 6 tasks to 9 tasks, then stayed almost constant, and then again it has increased. And one more thing was that we had this model of the human, simple model of randomized model of the human, that the human can perform we simply assumed that the human takes 9 to 12 seconds to do the task, and he follows the rule correctly if for all the initial tasks until 2 minutes, and then later on all the other tasks he leaves to the automation. So, and this model it kind of predicted the pattern, not exactly, but it came close. Okay, you mean this part? Yeah, I mean, yeah, that was the observation, but I don't have any particular reason why that is happening. Yeah. These are essentially measurements from 18 samples. And then we use these measurements, these functions, to do the allocation using the algorithms. That was the And then we compared this optimal allocation and blind allocation in the second experiment. And these were for 14 participants. So you can see that the blind allocation is costlier than the optimal allocation. And we performed a statistical test to see if this can be generalized. And in the worst case, we get a p-value of 0.002, from which we reject the alternate hypothesis. We reject the null hypothesis. The null hypothesis is that both will have same cost, and the alternate hypothesis was that blind allocation is costlier than the optimal allocation. So this is all well and good. So can we see if this works in a more realistic situation? So we considered this setup in a different study. We consider this scenario where you're scanning the horizon using two things. One is a radar and one is a PTZ camera, and you're scanning the horizon for flying objects. They can be birds and they can be different types of drones. Now you have an AI system which is processing the data, and you have a human operator whom you can call once in a while for some of the tasks. And now we applied so this was the setup. This is a PTZ camera, and this is FMCW radar, which was used to collect the data. This is an example track of a bird, and this is the example track of a drone. So now we had this kind of a setup. This is not completely integrated and real time. All computation was done offline. And we had a radar feature extractor, and then we had YOLO V7 object detection and classification for the PTZ data. So these are some examples of true positive on the top. It's not particularly visible, and these are false positives. So you can see they're false positives. And when we applied the referral scheme to this data, so these are some of the examples of the snapshots which were referred to the human. So these two are false positive. There is no object in this. And this is also false positive. This is interestingly false positive here and a false negative here. There is a drone here which is visible to the human eye when it is zoomed in, but it was not detected by the AI. So these are some of the, so it's still ongoing work. We are trying to implement this implement a completely integrated system to work in real time. This was computed offline. Yeah, so I wanted to leave you with some thoughts about potential future work which we all can think about. So can we think about real-time decision support systems? For example, where there are complex tasks and that require memory, attention, and executive function, and compound tasks having multiple subtasks. also modeling the fatigue along with mental workload. So for example, I wanted to show you this scenario where a real-time decision system might help. So you can see that if you go a little, so suppose somebody says that, as you can see, this person here is turning, and the driver seems to have not noticed this person. This is this is an accident which happened last month in Maharashtra, someplace in Maharashtra. So suppose if I say that I can come up with a decision support system which can alert the driver about this motorcyclist by showing him by marking him on the screen. Now, if you are a policy decision maker, and I come to you with such a real-time decision support system, how can you be sure that my decision support system would actually reduce the risk and not increase the risk in some other scenario? Here, maybe in the situation which I showed you, I might say that I see in this situation my system would have helped, but suppose you are a policymaker, you have to make a decision whether to approve my system or not. How can you be sure that this is actually reducing risk? Is there a formal way of verifying such a thing using some model-based, simulation-based verification methods? So, for example, there is some work going on for formally verifying neural network systems which have been trained for autonomous navigation, whether they are formally verifying whether they are following road rules or something like that. But in such a system, how do you actually formally verify, and with how much confidence? And also, given a system of rules, for example, the road rules which we have, this is just an example, does following the road rule system actually reduce the risk as intended? And given that set of road rules, if a particular decision support system is implemented, will it reduce the risk, and with how much confidence? These are like very open questions. Maybe some of you can think about them. Okay. Thank you.
Thank you very much, Dr. Kesav, for an informative talk. I request audience to ask questions if there are any. I think there are no more questions.
Okay. Thank you.
Thank you so much once again. And we also have arranged refreshments at the coffee hut. Feel free to continue your discussions while having a cup of tea. Thank you everyone for attending. Have a great evening.